Hello everyone, in this video we are going to see how to evaluate S-attributed definitions in bottom-up fashion. S-attributed definitions are those in which every parent node depends on the child node, or RHS values are used to evaluate LHS of the expression. To understand the evaluation method, let's try to take an example. So we are going to implement a syntax directed translation scheme for DES calculator. That means we have to perform some arithmetic calculations. To evaluate the expression, we have to take this example, that is 23 into 5 plus 4, using this scheme. So let's try to implement this SDT. To do so, first step is to write the grammar which will describe the inputs. So input is 23 into 5 plus 4 $. Dollar indicates end of your string. 23 multiplication is one of the value that we need to use in our grammar, addition and numbers. So to do so, this is the production which is listed here. First is addition. So if I add two expressions, I get a new expression E. Next is multiplication, which is there in the input. You can use bracket in case if I want to do addition first, I'll add a bracket sign over here. So one expression for bracket, and any number is represented with I. So what is I? I can be a recursion of I digit, or I can be simply digit. I tends to digit indicates it is only one digit, and when you have more than one digit, we will be using this expression recursively. We'll try to explain this with the example ahead. So for time being, let's understand this. I tends to digit is only for one digit, that is 5, 4, which are single digits, and I tends to I digit will be for multiple digits which form a number. Now that is our first step. In some examples, grammar will be directly given to you, so no need to use this first step. You can directly take the grammar from the question. Next is, we have to add semantic actions or rules to the productions of the grammar. Means with every production, we have to perform some additional action. So if we only use productions, we'll be able to only check the syntax of this expression. But we don't want syntax checking, we want evaluation also, answer of this expression. To do so, we'll add semantic actions with every production. So let's start with the last production, I tends to digit. So if I use I tends to digit, digit is already a value and it is indicated with lexval. So I have to use this lexval and store it in I.val. Val is an attribute for I variable. So this value will be the value of the digit. So if digit is 4, lexval is 4 and I.val will be 4, and accordingly. If you have multiple digits, you have to apply this rule, that is I.val in I1.val into 10 plus lexval. Let's take an example for this. Suppose I have two digits which are suppose 23. So if I want to make this as I, first is I tends to digit, and the next is I tends to I digit. So now first is 2, 2 becomes I, and next is 3, which is still a digit. So you have to take I digit, means 1 I, and this 3 is digit. So I digit becomes I. So this rule is to combine multiple digits to form a number. I can use this rule repeatedly as and when I want to make multiple digit numbers. Suppose your number is 234. So now I have got 2, which is digit, digit becomes I, digit becomes I. 3, I3, I digit becomes I. Now next digit is 4. So 4 is digit. You can make this digit as I, or you can make I digit as I. So I digit becomes I. So we'll combine these digits to form a single number as and when we want. So this rule is used recursively to apply the combination of multiple digits to get a single number. So now once I get this number, it is not sufficient to just club these numbers to get a club the digits to get a number. Instead, if we have 2, 3 and if we want to make it 23, 2, 3 are two separate digits. If I want to make it 23, I will just do like this, 2 into 10 plus 3. So that becomes 23. If I want to make it 234, I'll make first it 23, then 23 into 10 plus 4. So that will be 234 and it will go on like this. So the same logic is being explained in this. You are going to take previous value, multiply it with 10 and add the new value. So previous value, multiply it with 10 to get a new value. Previous value is 23 now. So take this 23, multiply it with 10, add 4 to get a new value. So this can be done recursively if you want to add more digits to your number. Once we get this, we got now I value. Finally, when you want to stop forming the clubbing of digits to get number, you will just substitute that integer I into E. So we'll call it as an expression. Then if there are brackets, this is E which we want, which is important for us, not the bracket. So we'll just take e1.val and store it in eval. Next is, if you want to do multiplication, we'll call this as first expression, second expression, multiply and store it in this E. So this is first value, second value, multiply, store it in eval. Similarly with addition. And finally, when we want to stop, if all expressions are checked, we'll print that value on screen, which will be final e.val. Now, to understand how to apply this semantic actions, let's create a parse tree for this input, and this is the next step. So now we will be trying to create the parse tree for the input 23 into 5 plus 4, and we have to do it in bottom up fashion. So we'll start with the first digit, which is 2. So now my first digit is 2. So we'll take this 2 first. When I got this 2 is a digit which can be seen here, and we'll be applying the productions in reverse order. Reverse order means digit will be replaced with I, and when I do this, this will be done simultaneously. So this is my digit. Digit is replaced with I. So the moment I make 2, which is my digit, into I, lexval becomes I.val. So what is lexval? 2 itself is a value of the digit, so we call it as lexval. So that we will store it in I. So with 2, we get a value which is called lexval. So lexval with 2 is 2, and this lexval is stored in I.val when I digit becomes I. So here with I get a I.val which is 2, right? So we got this 2 here. Next step is to take the next digit, which is 3. So I got 3 now. After taking this 3, the lexval of 3 is again 3. Now I have to club I and digit. So this is I and digit. I digit becomes I. So I and digit becomes I, and simultaneously perform this semantic action. So I and this digit becomes I, and I.val will be I1.val, which will be this, into 10, means 2 into 10, plus lexval. Plus lexval is 3. So this is 2 into 10 plus 3. So for this I, we'll get a value which is I.value will be 23, which is I digit I. So I digit gives I. I am done with this. So now next step is, you have got a star or a star in the input. So now 23 is done. Let's try to take a star here. So now in my input, the next symbol is star. So no expression, only on star which we can apply. Let's move ahead. Next input is 5. So let's take the next input as 5. After taking 5, again 5 is a digit. Digit becomes I. So 5 is a digit. Digit becomes I, and I.val needs to be calculated. So with 5, the lexical value of 5 is 5, and similarly the value of I will be this lexval, which is 5. So with 5 we have only one digit associated, so no need to apply this rule on this step. Now we cannot do I into I because there is no rule which will help us to do I into I. So now I needs to be made E. So now on this step we'll make this I as E. Similarly this I will be made as E. So whenever we make I as E, I's value will be put up in E's value. So this I's value will go in the E value. So this E dot val will be whatever I dot val was, so that is 23, and this E dot val will be whatever this I dot val was, which is 5. Now we'll multiply this E into E and we'll apply this rule now. E into E becomes E. So even into E2's value we have to multiply to get a new value. So on this step I'll multiply E star E to get a new node E. And whenever we get a new node E, to calculate this value, we use its children node values, which is 23 into 5. So E dot val is, we have to perform this multiplication now, so which will be 115. Right? After getting this, we have evaluated this much expression. So if you observe, we are drawing the tree, and along with that we are calculating the values as well. Next step is use addition sign. So this is my plus. Next is we have 4, which is again a digit. So 4 will be a digit which you will make it as I. So 4 will become I. When you make 4 as I, with 4 we have a lex value as 4 itself, and likewise that value will be assigned to I, which is I dot val will be 4. So this I dot val will become lex val, that is 4. Once we get this, there is no more digits, so no need to apply this rule. I becomes E. So this I becomes E, and we get a value for E, which is E dot val, nothing but I dot val, which is 4 here. Now we'll apply E plus E rule to get E. So when I apply this E plus E rule, I'll take first E1's value, E2's value and add it. So we can call this as E1 here, this as E2 here. For this E, this was E1 and this was E2, and likewise. Now this E plus E will be this value 115 plus 4. So here E dot val will be 119. And lastly, to end up, we have a dollar. So dollar indicates end of the input. So here we have got dollar, and when I club E with dollar, so E with dollar gives us S. So I got this S, and with S the action associated is E dot values printing. So we will be printing this value. So we will be printing 119 on screen. So we have created the parse tree for this, and simultaneously we have calculated the answer of this expression as well. This was possible with the help of semantic actions or S attributed definition. So if you observe, for every parent node calculation we have to use child nodes. This is I parent, this is child. E is parents, I is child. So we have to use child node value to calculate parent node value, and that is nothing but synthesize attribute. And everywhere we have used the same strategy of synthesize attribute. So this definition becomes S attributed definition, and evaluation is done in bottom up fashion. We have drawn this tree, but if I want to implement this in the compiler, we have to move on with some additional steps. So let's move to the next step. Next step is to implement the SDT which we have discussed earlier. We have to do two things: create a lexical analyzer as well as a bottom up parser. So, and the parser will invoke program fragments just to do the things that we have done before making each reduction. So now two things, one is lexical analyzer, another is bottom up parser. So first is how to construct a lexical analyzer. So to construct a lexical analyzer, first we'll pass our inputs to this analyzer. So the inputs are 23 into 5 plus $4. Job of lexical analyzer is to identify tokens and pass it to this parser. So it can be done all at once or one by one. So parser can call this lexical analyzer, and whenever it calls the lexical analyzer will give the token. So first token is not only 2, it is 2, 3, which is 23. So parser takes 23 and uses this 23 for the next step. Now next is, once parser got 23, it will ask for next input. It will again call lexical analyzer will send a star, parser will use star and perform the operation. Parser calls again, gets 5, lexical analyzer sends 5, parser uses 5, it will do evaluation, and this continues for till a dollar is encountered. Now once all the tokens are created and passed to parsers, or tokens can be created and sent to parser one by one, LR1 parser needs to be constructed. To construct this parser, we are going to revisit the same productions, but we will be now implementing the program fragment. Instead of just understanding instead of using the attributes, we will be using now concrete stack to perform the operation. So in earlier example, if you see here, we have got semantic actions which we have used. Instead of these actions, we will be using now program fragment. So in this action, we have used attributes. Now we will use stack. So val is the name of your stack, and top is the top pointer of your stack. So initially whenever you put lexval in ival, so this val will get stored in the top of the stack, and the name of that stack is val stack. Now next step will be, if you want to make multiple digits, like 23 we made. So for 23 we have 2 is already in stack, let's assume. So we have to pop this 2 from stack, multiply it with 10 and add it with 3. So value is already on top, which is 2. Multiply it with 10 and add the new value, which is 3, and performing this operation will push the new data on the top of the stack. If you see this bracket e bracket, and if I want to represent the same with the help of the stack, let's try to understand here. If you want to represent e tends to e bracket e, so we can represent the stack like this, bracket e bracket. Now this is the top, this is top minus 1, this is top minus 2. So brackets are not needed, because once we solve the bracket we will not be using them for further evaluation. So now we are only interested in top minus 1 value. That is what is represented here. We are interested in value at top minus 1 if there is a bracket. Now if there is multiplication or addition, we are interested in top as well as top minus 2 values. How? So let's take an example. E tends to E plus E. So if we have E plus E, this is E, this is plus, and this is E. So now this is top minus 1, and this is top minus 2. So at top we have an expression, at top minus 2 we have second expression, and top minus 1 we have plus. So no need to use top minus 1. Instead we have used here plus sign, or we can use here star, and we'll use top minus 2 and top values. Now let's try to implement this program fragment, which is a similar way of implementing this semantic action. You can say this is more abstract way, and this is the programmatic way of implementing the same logic. So now once we have written these program fragments, we'll try to implement the same with the help of stack. In this earlier example, if you see, we have written semantic actions and created the parse tree. But if you want to allow compiler to do this, means computer has to create this parse tree for us, so we have to be more specific while writing the actions. So we will not be writing actions like this for implementation, we will be writing actions in the form of a program fragment, and instead of drawing the parse tree, we will be implementing it with the help of stack now. So let's try to understand this. We have got an input. So input is 23 into 5 plus $4. Stack has two parts, state and value. So firstly, we are going to put the value. Stack will have the state. State can be expressions of your symbols of the production, and value can be the actual value associated with it. Production used will be adding as and when we have. So initially we have nothing in stack, no production used. We'll take this 2, we'll push it into the stack. So we have 3 star 5 plus $4 remaining. 2 will be pushed into the stack. So first 2 will go into the state. So your stack and value is 2 itself. So no need to write this. No production is used. If you see 2 is a digit, so digit becomes I. So we'll pop this 2 and we'll push a I instead into the stack. So now this 3 star 5 plus 4 will be as it is. We'll pop the 2 and we'll push a I. But with this I, the lex value associated will be stored in the value part of the stack on top of it. So value of I is 2. So what are we doing now is, instead of representing the stack with only terminals or non-terminals, we are going to represent the stack as a 2-part option. One is a state and another is a val. So when I say I, which is this I, its value associated is 2. And this is the top of the stack for now. So value at top is 2. That is what is said. Value at top is lex val, and lex val is 2 for us. So yet we have not used any production, but now I, we have used digit became I in this. So I can say I tends to digit is the production that is used because we have made 2 as I. Right? Now next step. Let's push this 3 into the stack, and remaining input is like this. So when I push 3 into the stack, the state becomes I followed by 3, such that 3 is on the top of the stack and 3 is its own value. So I will not change the value. Value is 2 yet so far. Now we have not used any production. So now 3 I3. I3 means I digit. So I digit should become I. Now for that I have to pop this I3 and push I. So here I'll be writing like this. I tends to I digit. Pop this I3 and push I. So if I push I instead of I3, whenever I pop I digit to push I have to take value at top, multiply it with 10 and add a lex value in it. So in this scenario, I3 and 2, how is the scenario here? I had I and 2 earlier. 3 is the new lex val. So what I have to do? When I have to push this 3, I have to first pop 2, which is on top of the stack. So I have popped the value on top, which is 2. Then I have multiplied it with 10, which became 20. And then I have added this lex val here, 3, which became 23. And this new 23 will be pushed back into the stack, so that my stack becomes I23. Right? So this is I23 now. So that is what is represented here. It will be I followed by 23. Right? So with I, value is 23. Now I should be E. We don't need any program fragment to implement because we are not changing any value here. So star 5 plus $4. E simply becomes I, no change in the value, so value is 23. And this is E tends to I. Next step is push this star into the stack. So we have got this, E star is the stack now. And in value, we will have just 23. For star, no value is associated. That means this was the original scenario. Now what will you do is, you will pop this I and you will push E instead of that. So your stack will be like this, E23. Now you are pushing the next symbol, which is star here. So no need to push any value in the values portion of your stack. And next is you will push the next digit here and value will be added here. Because star has no value, we'll keep this part as empty, which is here as dash, right? So here we have not used any production so far. Let's push 5 into the stack. So plus $4 is remaining, E star 5. So that will be 23 dash dash because 5 is the value itself. Next step will make 5, which is digit, as I. So now no production. Plus $4 E star 5, digit becomes I. So 5 becomes I. We have used this production, and here with I the value is 5. So it will be 23 dash 5. So what we have done now? E star I, and with I the value is 5. Now next time we'll pop this I and we'll push E on this step and it will continue. So now plus $4 E star, pop this I and push E. When we do this, no change in the program fragment, means no change in the value. And what expression we have used? Production is E tends to I. Next is push this 4. So $4, push the plus. So it is, before pushing plus sign, we have to just check, as E star E is the RHS of the production, E star E will become E first. And when we do this, that means E tends to E star E. So we have to pop this E star E and we have to pop the values also associated with them. So if we observe this here, originally we had scenario of this form. We have got E star E 23, no value, 5. This is top minus 1, top minus 2. When we make E star E to E, we have to do value at top, which is this 5, into value at top minus 2, which is 23. So we have to pop this 5, pop 23, multiply them, get the new value, which is 115, and push the answer into the stack. So E star E will become E, and this multiplication will become 115, and this will be the new top of our stack. So if we observe here, E star E becomes E, and 5 into 23 is 115. So we have made E star E as E. That is what said ki we have done the reduction, and simultaneously we have taken the value from top minus 2, multiplied and store it on the new top. So this is the value part of your stack, right? So now the same will be represented here. We will not have a star yet, and we'll take a value as 115. Now the next step is we'll push first plus onto the stack. So it will be E plus, and this will be 115 with plus, value is plus itself, no production used. Push 4, so you'll get E plus 4. And when you get E plus 4, it will be 115 dash dash, and no production used so far. Next is E plus 4, it will be E plus 4. For 4 is digit, make it I, 115 underscore, I's value is 4, and we have made I tends to digit. This production is being used. Next step is we'll make reduce I to E, which is I to E, and no change in the values because this is dash. So this is 4 as it is, and we have used E tends to I. Now E plus E, which is this, again you have to do same, top minus 2, add them and store the new value. So if you observe here, till multiplication we had this scenario, that is 115. Now top is E of 115. What we will do now is we will push here next step, which is E 115. We'll push plus, no value is associated. We'll push one more E, and the new value is This is at top, this is at top minus 1 and top minus 2. Take the value of top minus 2, 4, 115 like this. Add them, which is 115 plus 4, that will be 119, and store the answer back into the stack with E. So this is E, and the new answer that will be stored is 119. So this is 119 which we got here. So E plus E will be reduced to E. With the production, E tends to E plus E. And next is, we'll be getting the addition here, 119. Finally, we will push this dollar into the stack, which is E dollar, and E dollar will become, whenever we get E dollar, we have to make it S and we have to print the answer. So this is value 119, and now last step is to make it S. Pop E dollar and push S into the stack, and this 119 which we got, finally we have to print the answer 119. Let us summarize what we have seen so far. So to perform bottom-up evaluation of S attributed definitions, first we need to write the grammar to describe the inputs, after which we have to write the corresponding semantic actions, with the help of which we will be creating the parse tree. When the parse tree has attributes and values associated with them, this parse tree is called as annotated parse tree. To implement this in the compiler, we have to implement a lexical analyzer followed by a bottom-up parser. So a lexical analyzer will help in generating tokens, which the parsers will use to construct a program fragment. With the help of this program fragment, inputs will be evaluated into the respective solution. That's all from this video. Thanks for watching.